Yeah, let's just start switch the capacitor CMFB circuit. Switch the capacitor. Some people may not be familiar with the switched capacitor. Yeah, this switched capacitor is switched capacitor. This is a capacitor that is switched. Say, this switched capacitor is so there is a clock period, say something like a phi 1 phase and a phi 2 phase or something like that. So this is a time. So this is phi 1 phase. This is a phi 2 phase. Phi 1 phase, phi 2 phase. It repeats itself, okay? Yeah, during this phi 1 phase, this capacitor voltage is charged to some signal voltage Vin. And then during this phi 2 phase, this capacitor voltage is charged to 0 or some DC bias voltage. So during phi 2 phase, it loses signal information. So yeah, see, this is, for example, this is Tn, this is Tn plus 1. Yeah, during this phi 1 phase, the next phi 1 phase, this capacitor voltage is charged to signal voltage Vin again, and then loses that capacitor information. Yeah, this is a switched capacitor. Yeah, I have my time-varying input voltage here, Vin T, and then, yeah, during phi 1 phase, this NMOS switch is turned on, this PMOS switch is turned off. Yeah, this is phi 1 phase. Then, this capacitor voltage is charged to Vin T, right? This capacitor voltage is charged to Vin T. So it makes time to settle, right? During this time interval, this VA, this capacitor voltage is not Vin T. So yeah, something like that. And next phi 2 phase, yeah, phi 2 phase, this is phi 2 phase, right? This is off. This left NMOS is turned off, right NMOS is turned on. Then, at the end of phi 2 phase, this capacitor voltage is discharged completely, so capacitor voltage becomes 0. Okay? So let's just see. If I plot this, so I have a phi 1 phase, phi 2 phase, something like that. Then my capacitor voltage, yeah, will be, say this is a 0, and it will be changed to Vin, right? Vin. This is Vin. And then during phi 2 phase, it will discharged to 0. Phi 1 phase, it's changing, it's charged to Vin again. And then phi 2 phase, it loses something like that, right? So if I connect this one, those two nodes, this is my Vin waveform, right? So it will follow. At the end of phi 1 phase, capacitor voltage will follow Vin T, right? Okay. So, yeah, those phi 1 and phi 2 are non-overlapping clocks. So for example, my phi 1 looks like that. See, this is 0, this is 3.3, and my phi 2 looks like that. My phi 2 looks like that. Yeah. So those two transistors, M1, M2, they never turn on simultaneously. Because see, so it's a 0, 0 there, right? So there are some period both transistors are turned off, but they turn on, they don't turn on simultaneously at a single time point. Only one transistor is turned on, or maybe both transistors are turned off. There is no time period where two transistors are turned on simultaneously. Okay, so this is called non-overlapping clock. Question? Your question is how can I make non-overlapping clocks? Yeah, see, this is a 0, so it may turn on, say, this transistor may turn on something like where, see, for example, Vin is here. Vin is, yeah, this is my Vin, okay? Vin changes very slowly. For example, my Vin is 1 volt, okay? Yeah, M1 transistor turns on Vin plus VTH, right? It turns on during this time interval where gate voltage is larger than Vin plus VTH, right? Okay? Yeah, this transistor turns on this time interval. Yeah, this is Vin plus VTH, right? So their turn-on period never overlaps, right? If I make this one match those two time instances, okay? Yeah. Sometimes see, you can make it more safe. Say phi 1 is like that, and my phi 2 is like that. I just add a non-overlap time here, right? We can generate easily this one. Something like this, let's just say, this may be inverter. There is a 2-input NAND gate. This is inverter, okay? Something like that. If there is one clock, oops, sorry. This is a clock, just a regular clock. And then I can generate phi 1, phi 2 easily. This is inverter. You can find it easily. Say then my non-overlap time is 6 inverter delay. Okay, 6 inverter delay. Oh, there may be CK bar. Oh yeah, I think there is CK bar there. Okay. Those are CMOS inverters. This is 2-input NAND gate or NOR gate. Okay, so let's talk about more about the CMFB circuit. Sorry, switched capacitor. Okay, so this capacitor is a switched capacitor because during one phase, by one phase, it just gets some signal information from input voltage source Vin, and then next phase, by 2 phase, it loses all the signal information, right? And the next by 1 phase, it claims again, give me charge. All right. So my see, there is a by 1 phase here. So this is my by 1 clock, and then my capacitor voltage VA looks like see it loses all the information completely discharged during by 2 phase. So this is by 1 phase, this is by 2 phase, this is by 1 phase, right? This is by 2 phase. So this clock is just a by 1 clock, right? This is a by 1 clock. Yeah, give me charge. So it just rise up. Oh yeah, it's a so yeah. This voltage is say example. This is a Tn. So this is a Tn plus 1. So this time period is 1t. Capital T is the period of this sampling clock. Then by 2 phase it loses again to 0. Give me charge again. So yeah, this voltage is V in Tn, right? This voltage is V in, oops, V in Tn plus 1. So yeah, there is a current flow. Yeah, something like current waveform. This I in current may look like that. Say this is something like that. Something like that. This is a 0, right? It's a I in current, right? So this is 0. The amount of current integrated with the time, that's a charge, right? Charge. So this capacitor, it claims a charge every by 1 phase. And then it just dump all the charge to this ground during by 2 phase. And next by 1 phase, it claims give me charge again. All right? So effectively, it is like a resistor. This resistor just dissipates all the energy, right? By heat. It's the same as a resistor, because this capacitor loses all the energy during by 2 phase, and then claims the energy at every by 1 phase, right? So it is like a resistor. So what's the effective resistance in this case? The effective resistance is we can say effective resistance is this voltage V in times average value of I in resistor, I in. Okay, we can claim the same Q here. See, I can say yeah. So this is my average Q here. Okay, average Q. No, this average Q may change a little bit. So this is I in average, right? The integration of this thing should be same as integration of this Q, right? So yeah, what's the charge supplied during by 1 phase? Yeah, then it's easy because capacitor C is charged to V in T, right? This Q should be C times V in Tn. So this amount of charge is supplied to C at the by 1 phase, right? So this let's see. Yeah. So what's the average I in? That's Q divided by period T, right? This Q is only C times V in. Okay? So my equivalent resistance is V divided by I in average. Then, yeah, I in average is V is V in over T. C, this is nothing but T over C, right? I can say this is FC, clock frequency. Okay, anyway, this T over C is the equivalent resistor. So I can say, I can approximate that circuit, something like, where is my that circuit? Oh, yeah. So I can approximate this, where is my pen? Is it here or there? Looks like I found, I lost my pen. Should be around here. Maybe here. Oh yeah, here. Okay, I found it. So I can approximate this switched capacitor into an equivalent circuit, something like that. This is I can say this is a C node and this is a B node. Okay, so this is a REQ between C and B. This B happens to be connected to here. So this B can be connected to any DC bias. In that case, I can see something like that. Okay. This DC bias has no signal, right? It's the same as a ground. So I can approximate this switched capacitor into resistor of T over C. Okay. Question? Nope. Okay. Yeah, so actually, question is, this equivalent circuit is valid in long time scale. Say, maybe, let's just say, for example, let me see, this current is actually, we can say this current and that current. You know, this current looks like that, something like that. This current is just average, right? Average. So when this switched capacitor is connected to some large circuit, then some voltage, some output voltage, say, with the switched capacitor, output voltage will change something like that. Okay. Say only valid output voltage is this point. This point. This is a valid output voltage, right? With this approximation, the output voltage will be changing like this dot. Okay. Oops. Where am I? Oh. Yeah. This dotted waveform is from this REQ model. This green one comes from real circuit. Okay, so we don't care about the transient in this time point. We just care about this binary value. Okay. The following circuit samples only the value at this time point only. Okay. After it is settled down. So in a long-term time scale, yeah. So this equivalent circuit works in the same way as the real circuit. Question?
여기서는 저기 VB에 RC로 올라가면서 I-는 RC로 떨어지는 거는 이 모스펫 그 R1 저항이랑 C 값의 RC 값으로 보시면.
Oh, okay. Yeah. That's right. The question is this transient behavior. Yeah, it depends on those R1CL, the time constant of this exponential behavior. Yeah, it depends on this time constant. R1 is NMOS resistance when it's turned on. Okay?